Hi, this is Angela Galloway, and we are continuing in Chapter 10. We're still in 10.1. Last time what we did in the video before this, we looked at doing hypothesis tests using critical values. And so we're talking about proportions right now. In 10.2, which is another video, we look at doing hypothesis tests for means. So right now we're doing proportions. And what we were looking at here is that to be able to tell if our statistic is an extreme value or something that's unusual or statistically significant, those all kind of mean the same thing when we're talking about hypothesis testing. When we're looking for that, we were setting up what we called a critical value. We'd find a critical value, and then from that, we would determine if our statistic fell past that critical value or not. So if like in this case, we set up some sort of critical value. The critical value is based on our alpha level. So the alpha will be given to you in your problem. If you're talking about in real life, you would set up the alpha level at the beginning of your test. But in our problems, we'll get the alpha level. Based on the alpha level, we will use these different critical values here. These are the most common ones you're going to use. Now, these are all going to be z values. So they're coming from either the normal table. You could get them using your inverse norm on the calculator, but these really are probably the 5 most common that you'll use. It's rare to have like an alpha level of like 12% or something, different than 1, 5, or 10. That's pretty much what we're seeing here, the critical values for that. Now, it differs depending on if you're doing a one-tailed or a two-tailed. If you're doing a two-tailed test, it's more like the critical value that we used for confidence intervals, because for a two-tailed test, you put part of alpha in both tails. So you actually do alpha divided by 2. So that's why we have a few differences here with our critical values. But that's what we learned in the last video was, setting up our critical value, then finding if our statistic falls into that rejection region so we can reject the null hypothesis, or if it falls in the not reject region where we fail to reject. So we did those examples there. But now we're going to talk about the p-value approach for hypothesis testing. So really both of the methods that we use here, you would come to the same conclusion. They're just different ways of looking at it. With the critical value approach, what you do is you're given an alpha level. Based on that alpha level, you create a rejection region, right? And then you calculate your test statistic and you see if your test statistic falls here or if it falls here, and then you make your conclusion. With the p-value approach, what you're going to do is you're going to have your test statistic. You're going to put your test statistic on the sampling distribution that you're testing, and then you're going to find out what's the chance that I would get that statistic, right? And the way we find that, what's the probability that it would happen, is we do the area under the curve, right? Like we did back in chapter 7 and 8. So to find this area here, that is, the area that we would find from our normal chart or using our normal CDF, all those areas are the way we find that probability in the normal distribution. But that probability that we find now, the area down here, that is going to be called our p-value. Okay, and so the p-value is the probability that we would get a value as extreme or more extreme than the value that we got. So it just means, you're finding that area related to the statistic you got. Okay, now the p-value is always going to be between 0 and 1 because it is a probability, right? So it's always between 0 and 1. Our area, the area under the curve, the total area is 1 or 100%, right? So it's always between 0 and 1 or 0 and 100%. The closer the p-value is to 0, the stronger the evidence is against the null hypothesis, right? Because the smaller the p-value, the smaller the area, the farther away our statistic is from the null hypothesis, right? So in the middle here, we have our null hypothesis proportion, okay, the proportion that's in the null hypothesis. If we get a statistic that falls, let's say here, okay, then our area here is going to be pretty big, right? Because it's fairly close to the mean, so there's a large amount of data that still could fall to the right of our statistic. So this would be a large p-value, right? A large area, which would tell us that the result we got was not that unusual, right? So we would fail to reject. But in this case, if we were this far away, this is a very small area, right, because we're pretty far away from the mean, and so there's not much data left out here in the tails. So it's very unlikely to get a result out here, which would give us probably enough evidence to reject the null hypothesis. All right, so how are we going to determine if our p-value is small enough or not? You know, if our area is 7.07, is that small enough, or 0.15, or, you know, when do we decide if that area is small enough? And so you can probably figure out what we're going to use based on what we used over here. We're going to compare this area to alpha. Okay, so if the area is less than alpha, then we're going to say it's small. Okay, and then we're going to reject the null hypothesis. And we're going to see more about that here. If the p-value is less than alpha, we're going to reject the null because that means it was far away from what we expected the mean to be, and so we are going to reject. If the p-value is more than alpha, then we fail to reject because we're going to say we don't have enough evidence to reject the null hypothesis. So even though our statistic may have been different from what our null hypothesis said, it wasn't different enough. The difference probably could have been attributed to just sampling error, right? So we look at how our p-value is going to be calculated. Our p-value, if we're doing a left-tail test, is the area down here. In a right-tail test, it's the area up there. If we're doing a two-tailed test, your statistic is either going to fall, you know, on this side or on this side. You're not going to have two statistics, but it's going to fall here or here. But because we're doing a two-tailed test, you actually have to double that p-value. So if you got a statistic over here, you would calculate this area, but you would also need to calculate the area that it could have had if it had fallen on the right side, okay? So you end up doubling your p-value if you're doing a two-tailed test, which does make it harder to reject the null hypothesis if you're doing a two-tailed test because you do have to double your p-value, which is obviously going to make it bigger. So, you know, that is one of those things when you're setting up your hypotheses, you want to think about, you know, do I want to do a two-tailed, or could I maybe just do a one-tailed? So this is what we're doing. If the p-value is less than alpha, reject the null. If the p-value is greater than or equal to alpha, do not reject the null. So the saying that sometimes they'll use is if the p-value is low, then H sub O must go. Okay, and how we know the p-value is low is that it's lower than our alpha. So it's smaller than the alpha that we have set up. So here's just a few examples comparing p-values to alpha. Here our p-value is 0.04, alpha is 0.05, so this is smaller than that, so we're going to reject. This one here, p-value is 0.5, alpha is 0.05, so we'd fail to reject, right? This is much bigger. This is going to happen 50% of the time. This says, you know, anything that's going to happen less than 5% of the time. So that definitely we would fail to reject. Okay, so doing p-value tests, you know, when we're doing that with our hypothesis test, actually can be a little easier because our calculator actually will give us the p-value. So sometimes students actually like this method better because the p-value is something that your calculator gives you. When we were doing the critical value test, you know, or the critical value way, you could find the critical value using your calculator, you know, using the inverse norm or whatever, but you still, you know, had to find that kind of the extra step after you found your test statistic, find the critical value, and then compare the two. But here we'll show you how you can just use this one proportion z-test in your calculator to get your p-value. So it says in a recent year, 73% of first-year college students responding to a national survey identified being very well off financially as an important personal goal. So then you took a sample of 200 people, 152 said that they think that goal is important. Test the hypothesis that the proportion of first-year students at this university who think this goal is important is greater than the national value of 73%. Okay, so greater than tells us that the alternative hypothesis is going to be a greater than, right? The null hypothesis is always an equal to. We're doing proportions here. One way to figure that out is if they don't give you a standard deviation, then you're probably doing proportions, right? Because we need a standard deviation if we're doing means. But for proportions, we're looking for, those percentages or 152 out of 200, that kind of gives us an idea we're doing proportions. So our null is p equal to 0.73. Our alternative is that p is greater than 0.73. We can calculate our p hat here. P hat is 152 over 200, which is 0.76. So at this university, 76% of their samples said they thought being very well off financially was important. Nationally, 73% said that. So we're wanting to see if this is a statistically significant difference or if that difference, that 3% difference, is really just due to sampling error. So our test statistic here, remember we do p hat minus p from our null hypothesis divided by, this is our standard deviation of the sampling distribution. We use p sub 0, which comes from our null hypothesis. So we're using the null hypothesis parameters to calculate this sampling distribution and figure out, where would this statistic fall if this was the true mean of the distribution. So we plug all that in and we get 0.96. Then to find the p-value, we would do it just like we did in chapter 7 when we were trying to find an area. If I said the z is 0.96 and find this area, you could use the normal CDF and go from 0.96 up to infinity. The mean is just 0 and 1 in this case because we're doing the normal distribution once, or the standard normal once we're using z's. Or you could do, you just use your chart, look up 0.96. It always gives you the area to the left. So you would subtract that area from 1 and you get 0.1685, and that's going to be your p-value. That's the area. So what that tells us is the probability that we would get a statistic of 76% or more is 0.1685. So that would happen about, 16 or 17% of the time. Not really that unlikely, right? But to be able to tell if it's unlikely enough or not, we're going to compare it to alpha. So here, our significance level was 0.10. So we wanted to reject anything that happened that could happen less than 10% of the time based on sampling error, just due to sampling error. This is going to happen almost 17% of the time. That is greater than alpha, right? Greater than the 0.10. So we fail to reject. We're saying that it's not far enough away. All right, so how do we do this on our calculator? So on the calculator here, we're going to go to stat. Nope, we're going to go to second. Yes, we are. I'm sorry. Stat and tests, and go down to one proportion z-test. So right here, in chapter 9, we did intervals. So we did one proportion z interval. And then when we're doing hypothesis test, we do one proportion z test. So go to number 5. Our p sub 0, so that's what's in the null hypothesis, is 0.73. Our x value is 152. Our n is 200, right? So that's just coming from these right here. And then you have to tell it what your alternative hypothesis is. The reason why you're doing that is because that's how it's going to know how to calculate the area. Because when it finds the test statistic here, when it finds that z, it needs to know, do you want this area or this area? Or are you doing a two-tailed test and you need, both of these areas? So you have to tell it that. So that's the one thing that I was saying, that you have to know how to set up the hypotheses on your own. Your calculator can't do that part for you. But once you've got it set up, your calculator can help you to find the test statistic and the p-value. Okay, so this is not equal to, this is less than. Okay, so we're saying that here, this is our p is less than 0.73. P is greater than 0.73. So you just pick which one you want. So ours is that one, and calculate. All right, so you can look up here and see what your alternative hypothesis should look like, and that's what ours looks like, right? The proportion is greater than 0.73. So you can always kind of check that to make sure that your p-value is being calculated correctly. It gives us the z here, so that is our test statistic right here, the 0.96. Of course, that was rounded a little bit, but that we got the 0.96. The p-value is 0.1696. Now they're going to be a little different because remember our this here is the exact value, okay? Because the z is not rounded and they find the exact p-value. When we're using our chart, on the normal chart, 0.96 is all we can look up because it's only rounded to 2 decimal places on our chart. So these are going to be rounded a little bit, but they're going to be fairly similar. Either one that you use on your homework should be fine, or on a test, because MyLabs realizes that some people are doing it with the chart, some are using their calculator, so there'll be more of a wiggle room there for your answers, so that's why on some of the problems, if you miss it, you might see that there's several different possible answers, and that's why. It's because, we've got some rounding issues here depending on if you're using the chart or if you're using your calculator. So this would be the p-value there. And then again, that of course is greater than alpha. So once you get the test statistic, which you can get from your calculator, you can get the p-value from your calculator. And then you would use your alpha level compared to the p-value to determine if you would fail or fail to reject or reject the null. Okay, and then we'll get into some more of these p-value type tests when we get into the next video in 10.2, because most of those I do on the calculator, just so you can do it that way. But if you wanted to, go back here, if you do any of these on the calculator, like let's say we did this one on the calculator, so go back to stat and test and one proportion z test, so number 5. Here our p sub 0, so our null hypothesis is 0.5, x is 275, and n is 500. The alternative here was not equal to, right? And then we're going to calculate. All right, so we get our z here, the 2.24. It gives us a p-value of 0.025, which we didn't calculate the p-value here, but we could use this p-value to compare to alpha. Alpha is 0.10. Our p-value is 0.025, which is much smaller than alpha, so we would reject the null hypothesis, right? We got the same outcome when we use the critical value. Okay, so using the critical value, our test statistic fell farther away than the critical value did, so we would reject. It fell into the rejection region. So since it fell in there, we reject it. So you're going to get the same conclusion either way. It's just whether you want to use the critical value and compare that to your test statistic, or if you want to use your test statistic to calculate a p-value that you can compare to alpha. Okay, so either way is okay to do. You should be able to do either one on your homework, or on a test, or whatever. You could do either one, because really the conclusion is what you're trying to get to. So the p-value is the p here. The p hat is just, your test statistic up here, or your statistic, and then your p is your p sub 0 is what's coming from your null hypothesis. All right, so that's how we do p-value approach, and then also the critical value approach. In the very last lecture video, which is the next one on 10.2, that one will go through how to do hypothesis test for means. And so for that, we'll be using the t-test on our calculator. All right, so if you have any questions over Chapter 10, please send me an email. My email address is angela.galloway@kctcs.edu. Thanks.